table's not too messy. And a bit more.
Does it work? No? Sound check. 1, 2, 3.
There's a 10-15 seconds delay here. So.
Yeah. Does it work? Wi-Fi thing. All good? Okay. Everyone, greetings from Oslo. After 2 years, I'm so glad and excited. We're finally back to normal, and this is our very first experience with in-person gathering. And so a big welcome to both our participants in the room and participants all over the world. So our stream is about to start in a couple of minutes, just to give a bit more time for people to show up and get connected. While you're waiting, you can visit my GitHub page to download today's presentation slides and today's R code. Very quickly, I will show you the address, so don't stress if you haven't done so. It's going to be a very gentle introduction, so relax. This is the first time we are gathering, so it's going to be...
I guess we don't have a microphone or anything.
So, like...
Then he has to speak louder. We don't have a mic in this room, that's correct.
All right, so I'm going to shout a little so that everybody, especially at the back, I'm so excited that we have so many people showed up because I was expecting 2, and then we have 20. So I was just like, yay! Already. So wait for Henrik to give me a...
So we're going to let the stream be dead for a little bit, just so that we are completely set up before we start the event. So we'll be back in a bit.
Everybody, welcome to the first Oslo Use Our Meetup event in person. That's all right. It's more important here. Some familiar faces, some new faces. We are really excited to be back in person, to be able to meet all of you again. Finally. One applause for yourselves. Man, this feels good. Really excited to see all of you here. I know it's not the best weather and everything, and we're still figuring everything out with the new location. Just bear with us. Also, you guys bear with us. We'll only get better from here. And thank all of you, all in person, all joining us from all over the world, so much for really sticking with us during the online time, or only online time. We're still online, we're hybrid now. During the pandemic, thank you so much for supporting us, for joining us, for volunteering, being forced to volunteer to give presentations on our events. It's truly, truly, truly appreciated. Today, I can click, excellent. Today we'll have a great presentation from Tony here. He'll start soon, so hold your horses for a moment here. About missing data. A topic that I love and hate at the same time. If you've ever worked with missing data, you can relate to that feeling, I suppose. So I'm very excited for today's presentation. As a bit of a spoiler, because we haven't yet announced it, because we haven't fixed the room yet, but we can spoil that next time. We are lucky enough to have the good people from FHI presenting for us. She will present it's an FHI internal system, isn't it? Sykdomspulsen,
yeah,
right?
It is.
Yeah. Heard great things about it with all sorts of package development there. I mean, that will be goodness as well. And before we start with your presentation, as always, if you think you can imagine that there's something in R that you're glad to do, that you think is really cool, and others should see it, here's your stage. I like to think we're all friends here. This is the friendliest territory you can think of. Next week, I'm at a scientific conference abroad. This is probably the opposite of what should happen here, right? When I'm at scientific conferences, it's like a pit of snakes, right? That's not what we are trying to be here. We try to represent the values of R and its community, and there's literally, I'd like to think of this here as a safe space for our programming. So please reach out to us, either to Bethan, to Henrik behind the chair, or to myself, Raul. Get in contact. Don't be afraid. There's a really low threshold here. Almost anything goes, as long as it's R related and not offensive, I guess. There's a code of conduct. But yeah, get in touch with us. And with that, Tony, the floor is yours.
Thank you.
I'm excited. And sorry for moving around so much.
Thank you. I'm actually a living testament, like anything goes, right? So Henrik approached me multiple times until I said yes. So here I am. Originally, I was planning for a Zoom session, and I'm so glad that that didn't go through, and that get postponed multiple times. And I'm going to be the first person who get to stand here today and share this room with everybody. So today, we're going to share this experience with this new package. This is actually a pretty old package, pretty well-established package, mice, multiple imputation using chain equation. And they end up with a very neat, cute name, mice. We're small, but it holds lots of promises. So in today's presentation, I'm going to break this chunky session into blocks. So in particular, we're going to have 3 blocks. The first block, section 1, is going to be the background, mixing data, oops, I need to stand here. I'm a teacher by training, so I walk quite a bit. So the very first block is going to be the background, missing data, the mechanism, what caused the missing data, and what do we do? The macro, the big picture. Then the second chunk is know thy data, know thy missing. We're going to inspect our data set, our variables, to see where the missings are, how many are missing, how the missings are related to each other, before we move to the third chunk, the third section, and that is, okay, now we have a very good understanding of what happened to the missingness, where the holes are. How do we deal with this, and how do we analyze this imperfect data set? So 1, 2, 3 chunks. And at the very last chunk, I'm going to share some resources with everybody. Now we conducted our analysis. We have beautiful results. How do we communicate to the wider community? How do we document this is what we did for our multiple imputation? So there's actually template paragraphs you can copy paste and change it a little, followed by a small library I have collected personally and with all the DOI, and it's all clickable. So that will hopefully serve as a starting point for additional reading and additional resources. All right, so let's start with our first chunk of today's presentation. I have saved today's presentation and today's R code onto my GitHub page. So if you haven't done so, you're welcome to download both the PowerPoint slides and .r file from my personal GitHub page. While we are talking, users can also prepare your R package by downloading mice, beam, mass, and lattice for, especially if you want to sing along, if you want to execute the R code to see whether it agrees with my slides. So you probably will need all these packages. So install them if you haven't done so. And today's main package is going to be mice. So we can do that while we start chatting with a background story. I became interested in missing data pretty much from a course assignment. I was doing my master back then, also in Center for Educational Measurement with Herrick. So part of our course is to investigate students' perception of teacher unfairness. So that was one of the questions from PISA 2015 questionnaire. And let's have a look at this questionnaire. During the past 12 months, how often did you have the following experience at school? The teachers called me less often than they called on other students. Teachers graded me harder than they graded other students. Teachers gave me the impression that they think I'm less smart than really I am. My teacher disciplined me more harshly than other students. My teachers ridiculed me, blah, blah, blah. So this is one type of question that is the opposite of socially desirable. It's like, did you experience any of the following? Sensitive questions. And when I downloaded the data set, I observed that there's lots and lots of missing data. Traditionally, you would just like throw them away, right? Because you just say, well, RA removable complete case. But then I noticed I can't do that this time. Why do you think I hesitated? Especially given the nature of this type of research question. What's wrong with deleting an A and A's? Yes. Shout out.
A lot of people might be uncomfortable answering all the questions, so they prefer just to skip all the student one like, and they could be a lot of questions that are missing just some of it or not all of it. So you can skip all of it because it is quite different.
When you ask socially sensitive, direct question, people feel uncomfortable and then they skip. Who are more likely to skip? those with or without adverse experience. Do you see, it's not equally likely, is it? In particular, students who experienced or witnessed unfair teacher are more likely to fall into the, if you have nothing good to say nothing, right? We learned this from our parents. So this is social desirability is always latent behind. And so this problem is not only things go missing, data gone missing, but it is going missing in a very interesting pattern. It is going missing with a probability that depends on the actual measure we want to measure. If you keep deleting, if you keep throwing out, or if you're missing, I ignore you, you're going to end up with an overly rosy picture. Oh, all teachers are brilliant. There's no teacher unfairness, right? So that was actually my motivation. I was like, I can't just naively say an A remove equals to true and then continue with the rest of my assignment because I'm going to get, yeah, of course there's no problem because you deleted the problem away, right? Okay, so that's one motivation, and that kind of already led us into this second slide, and that is there are three types of ways, let's say, data can go missing. One of them is the most, the least bad way, and that is things gone missing in a pure random fashion. They go missing at a fixed constant probability rate. It doesn't correlate with anything. The example I gave is the other extreme. The column or the variable that has gone missing depends on its own value. That's the worst. That's the other end of the spectrum. And in the middle, the probability of this variable goes missing does not depend on its value, but depends on its neighbor's value, but its neighbor is fully observed. So that's the three different ways. The worst way, the least bad way, and the way in the middle. And they have a name. This is all attributable to Rubin in 1976 when he was the first author who systematically documented and he pretty much put this into a library of thoughts. So he named the least bad missing completely at random. While if the probability of this column goes missing depends on other columns, not itself, missing at random. So theoretically, we can actually study how you go missing with full information. We can retrieve how you have gone missing. While the last case is rather hopeless. It's like, now you gone missing is irrecoverable. In most of our research, we are dealing with this good and intermediate case. If you suspect your dataset suffer from strong missing not at random, what do you do? Out of practice, the straight answer is complicated, it depends. But the short answer is throw in lots of covariates. The more covariates, the more demographic variable you can throw into your model, the more likely you are going to pull, or you are going to pull yourself out of mud. You're going to pull yourself more away from this bad, worst extreme of the scale, more towards this less bad scale. So if you do have suspicion you are here, pull yourself back up. Because this is pretty much where all this algorithm, especially mice package, would work best. So it's either completely at random or at random. What you see here is actually a toy data set I created. So if you have a look at code 2, if you just execute code 2, you can replicate this, this picture. In my code, you can actually see how I created such missing mechanism. Completely at random, I say with 0.5 probability, throw away whether you're missing or not, right? So complete at random at one constant. While missing at random, the probability y2 goes missing, the second column goes missing, depends on the value of y1. Well, y1 is not. Y1 is totally observed, while y2 goes missing under this nasty scenario. It depends on itself. Unsurprisingly, the distribution, the observed versus missing, observed versus missing, becomes increasingly out of whack as we move from a good case to a bad case. Now, the big picture philosophy of multiple imputation. We're going to start with the original dataset, imperfect dataset with holes in it. We're going to split this dataset into parallel universes. In this picture, I split into 3 different versions. And then for each version, I conduct my analysis separately. So I repeat my analysis 3 times. Then I pull my 3 analyses back into 1, this time with a standard error, with a confidence interval. That reflects our uncertainty about this back-guessing process. Original with whole, 3 versions, 5 versions, 10 versions, how many parallel? Each are complete, but with guesses. Separate analysis, pull back in together. If the original data set is not missing, then all these parallel are identical. However, if the original is a whole, you're going to see all these 3 versions, 5 versions, 10 versions, they differ a little. How much they differ reflect how certain or uncertain we are about our guesses. Then when we pull things back together, we're using Rubin's rule. You're going to hear this quite a lot. It's all done behind the scene. You don't have to suffer from the complicated formula. Thankfully, all computers are doing that for us. The attractiveness of Rubin's rule is it'll give us the correct standard error, therefore the correct confidence interval.
I'm keeping an eye on the chat, and there was a question.
Yes.
That I'll just pass along. Regarding the last mechanism, how could a missing data point depend on its value? What does that mean in plain language?
So the question is, how can dataset gone missing with probability of the underlying value? That's actually exactly what this teacher unfairness feels like. If the actual value is high, I experience more teacher unfairness, I am more likely not to tell you. While if I experience less of a teacher unfairness, I'm more likely to report it. So you try to measure how good or bad and how much you experience teacher unfairness. And this high-low actually directly correlate with the probability that you actually get a missing an NA in your spreadsheet. And that's what this missing not at random feels like. And that's the worst type of missing. So it depends on the underlying actual value, which is not observed. Yes?
Actually, a question related to that. So you said that if you add more covariates, then you can pull it to the other scenario. How can you add more covariates? Is it like when you do the survey or later? Or?
Yeah, so what happened is there's actually no straightforward solution. Norman Rose from Germany, from University of Vienna, he actually did a whole PhD on it. I read his PhD, and the conclusion from his many years of project is it is super complicated, but a quick and dirty rule of thumb, we all love practical advice, is throw in lots of covariates or throw in lots of rescue or peripheral information. The more peripheral you can lend to R, the better job R can seek or look for patterns to find someone who are most similar to you with the most similar answer responses. Therefore, you are probably more likely to be here. So the more you can help R, the better R can help you. So that's his advice. It's not theoretical. It's like here, due to this formula, partial this and partial that, you should do that. But it's much more of a practical advice. Yes.
Actually, I was wondering, like, how do you get these covariates? Like in the case of pizza, you would ask the people's age, or
That is already in the background questionnaire. Yeah. Such as your parents' education, your parents' job code and everything. So quite often that's at the beginning of the spreadsheet. Yeah. So throw them in. Help R, help you. So that's pretty much the big picture. And multiple imputation is particularly attractive for me because it separates missing data problem from the substantive scientific problem. And that's the modulation advantage. You can actually, for the first stage of your analysis, you don't need to think about answering your research question, but focus on splitting parallel analysis, then pull back. Then you can divide and conquer. Missing data is missing data only. Once it's been filled back in, then substantive scientific question can come back in with the correct standard error. Right? So this out of logistics, this is also another rather attractive approach. So, can I move on to section 2, or I should invite more questions, especially from YouTube? YouTube is pretty happy. Yes?
So when you say split the data, does that mean that you make multiple copies of the data, or you even split it? Or?
Essentially. So what happened is, so the question is, what do you mean by split the data? It's essentially a copy-paste of the data set 3 times, 5 times, 10 times. If the original cell is already there, then that's identical. 3 copies, 5 copies. If the original is a missing box, this missing box will be filled in with multiple guesses, and they may not be identical. We will see very soon what they look like in actual computer screen. They differ up to our, they differ up to our uncertainty. The worse our guesses are, the more those 5 different versions are going to differ by. If by throwing in lots of demographic, by throwing lots of peripherals, the computer is able to very accurately predict what these missings are, you will see those 5 numbers, they are very close. 27.3, 27.2, 27.5, 27, they're all 27 something, they differ by a little. That means you're very, very confident. You are around about 27 something. So that's where I mean by the correct standard error can be constructed. So uncertainty is carried with us throughout our analysis. Oh, this doesn't really help, does it? I hope most of our participants have a copy on your computer screen to overcome this. It looked better when I was in my office. Now, so
if you can zoom in.
Yeah, that's a good idea. I just learned that from Henrik actually. Can I make it bigger?
I don't know how to do that.
This is the biggest. All right. So if we can also run this on our computer, what we will see is we can read in this N-Haynes data, and if you press enter, you're going to see this data set is a 2A data set. It's a very small data set. It only has 25 patients in it, and we want to know the patient's age, body mass index, whether they have hypertension, it's a binary yes/no, and their cholesterol level. So we can imagine that's 4 different columns with 25 patients. Yes.
There was another question in the chat.
Yes.
just to mention that the live stream is about 30 seconds or a bit more delayed to our live event, so I'm not always nailing the timing here.
All right.
The question was prediction of missing data. What about reproducibility then?
Use seed. Replicability, as you will see throughout my slides, I have seed equals to, for teaching purposes, I want you to have exactly the same plot as mine. And for real research, you can do like a sensitivity analysis, right? You throw in the seed, you change your seed, hopefully you don't change your result. Otherwise, your first result could be quite a fluke. All right, so if you read in the dataset, you press enter, and you will see, okay, this dataset is a very small scale patient survey with holes, not everywhere, but like age, for example, perfectly observed, not a single hole. But then body mass, cholesterol, some patients refuse to give you such information. Some of them are ordered, categorical, some of them are binary, and 2 are numeric. Good, know your data. Now, if I execute md.pattern followed by this dataset, what we're going to get is a pattern plot. And that is, if I can zoom out, oops, that's what we get on the right-hand side, right? So MD pattern, what does this picture mean? We have 4 different variables: age, hypertension status, body mass index, and cholesterol level. For 13 patients, not a single variable is missing. For 3 patients, cholesterol is missing. For 1 patient, BMI is missing. 1 patient, both are missing. 7 patients, only the age is given. Hopeless for the rest. That's what this picture is trying to tell us. In multiple imputation literature, we always use blue for observed. We always use this reddish pink for missing. No missing. 1 variable is missing. 1 variable is missing. 2 variables are missing. 3 variables are missing. Right? So this is a very bookkeeping device telling us what the missing feels like. And if we type MD pairs, what we get is a more nuanced plot. So you can execute that on your little screen. What you see is you see RR, RM, MR, and MM. R means observed, the blue. M means missing, the red. So that's pretty much the same information in tabular form. And if I can focus on body mass index versus cholesterol, this pair, because those 2 are both numeric variables, you will see you have 13 completely observed pairs. The cholesterol, yes, I have questions.
Yes, there was one more question in the chat. And that was, how can we tell if the missing data mechanism is missing completely at random or just missing at random? Is there any statistical method for doing this?
Whether we can for sure mathematically using 1 test 5% confidence saying whether this is more like here or here, the answer is no, unfortunately. More honest answer is quite often theory, substantive scientific theory, scientific intuition would give us more guidance on you're more likely to be complete at random. One possibility for completing at random is we scientists assigned people to different groups. For example, in education, that's my research. We as examiners can actually choose to throw students into 46 different booklets. They are all parallel in design. They differ by a company name. They differ by a date. But then they are all the same 46 comparable exam booklets. Then what happened is, for students who receive one booklet, the rest of 45 will be missing. In this case, this sort of missing, out of intuition, out of theory, we know what type of missing is it. Completely at random or at random. I, the examiner, I, the scientist, assigned, caused such missingness. What type of missing is the best type or the worst type? More likely to be the best type, missing completely at random, right? So sometimes theory, practice, intuition will guide us, although there's no statistical test to tell us. Yes?
I would say if the dataset is large enough, you could probably look at how many are missing on different types of variables, and then you could probably do some clustering to see if they seem to correlate.
Yeah, our next plot actually will look like this. So in the ideal situation, if you have a missing complete at random MCAR, you would, in theory at least, observe the green and the blue, the blue and the red should roughly align. So that's another, again, we don't have a definite 5% cutoff, but we do have visual guide. We have theory, we have practice, we have intuition, and we have visual. This is what I mean. So, in particular, I'm interested in this cholesterol versus body mass index combination. So I'm going to put it up, and I'm going to form, this time, instead of looking my missing pattern at the spreadsheet level, I'm going to examine the variable level. So that's a cross missingness between body mass index and cholesterol level. So now it's more of a micro level examining the missing pattern. So I plot cholesterol on one axis, BMI on the other. That's how I cross them. Then I order computer, please give me a margin plot. So I use VIM library and margin plot. Then this is what I get. So how do I read this cross plot? What does it mean? So we see there are 20, I think it's 25 blue. Blue means it's observed for both the cholesterol and BMI. So that's why I have the definite coordinate. I know where to plot them. But then I see 3 dots here. I see 2 dots here. I see some red numbers. What do they mean? This red 9, let me zoom in. This red 9 tells us that BMI, so if I can zoom out a little, 9, that's the vertical. Vertical's BMI. 9 BMI are missing, while this 10, that's pointing horizontal, 10 cholesterol is missing. And this 7, this red 7, saying there are 7 pairs that both cholesterol and BMI are missing. Then we have this distribution plot, the box plot. In an ideal situation, should cholesterol and BMI pair gone missing in MCAR, completely at random fashion, those two colors should share very similar patterns. The more they differ, the more your data is talking to you. This is very unlikely to be an MCAR. So it's more likely to be an AR, MAR, or even worse, an MNAR. Yes?
In the plot, there are also white dots.
There are also
White dots.
white dots. So we have one question from the participants. And yes, so the question is, what are those white dots? We observe their position or their coordinate for cholesterol, but we do not observe their coordinate for the vertical, which is for BMI. So this is how I visualize missing. So if it's X, the horizontal, I know where to plot, but the vertical I don't. I throw them down here. So that's the 1, 2, 3, 4 There are 10 of them, so there's a bit of overlap.
But they are what you would consider outliers in a box plot. So they're outside the area where you would summarize the data with the box plot, and then it goes up as data points.
That's what they were calling it.
Can we move on to, I want to do something. Now I know too much about, stop telling me I have problem. I know I have problem. Now, can we do something about such problems? Well, that's where mice comes in. That's why we're here today. This is how you use mice. You turn on library bracket mice, end bracket, and press enter. Now you're ready to order your mice magic. So, mice, open bracket, throw in your data set, close bracket, enter. For me, because this is the teaching purpose, I've set seed. Oh, you want me to make it bigger. So this is the basic syntax for implementing multiple imputation. Mice, data set, followed by options. I put two options here. One is I don't want n plus. I don't want R to behave like n plus by giving me all this like a vomit of different iterations. I don't want to see it. Can you just like do that behind the scene? And I set the seed so that everybody gets exactly the same. So it's a very parsimonious syntax. And I say save the result and print the result for me. And then this is what I get. R is very reasonable. They give me enough and just enough information about what it was doing. So, print impute. Now, I get a class called MIDS. MIDS stands for Multiple Imputation Data Set. So, imp is MIDS in nature. So it's not one data set, it's 5 data sets. You might say, oh, how do I know it's 5? 5 is the default. If you don't say how many you want to order, mice will give you 5. And later, I will show how we can actually order more. Yeah, there we go. So in this multiple imputation data set, you have 5 layers stacked together. And this is the method mice just used to impute. Out of the 4 variables, we inspected the variables before. The first variable, age, doesn't have anything missing. So don't worry about it. Mice is smart enough to skip it. BMI, hypertension, and cholesterol all contain missing value, and R will try its very best to guess what's the best method to use. Here, R said, I probably should use predictive mean matching. I'm pretty happy with it. Predictive mean matching, PMM. Again, later we will see how to customize mice. And predictor matrix, which variables are used to predict which variables. The column or the left are the variables are used to predict what is missing. That's where the previous question kicks in. It's like, how do we feed all these demographic variables, peripherals? We feed them to the left, and then we tell R, the top are the names that are missing that I want you to predict. Input, output. All right, so that's the first inspection, first experience with our mice package. Yes?
In one of the cases, the R will use itself for imputation.
R will.
The variable will not be used, like the diagonal is 0. But what if being close to a particular, let's say, range within that value or that variable would be also informative to impute?
You see a diagonal of 0, that means you are not using yourself to predict yourself.
Yeah.
That's not very.
Because like in the worst case scenario.
Yeah. Oh, you mean missing not at random?
Yeah.
For missing not at random, we don't. The entire mice package operates based on missing at random or missing completely at random assumption. So if you know you are in missing not at random, you need to pull yourself out of mud to be safe enough to use mice. Mice cannot pull you out of the mud. So that's why you really want to argue in your typing. It's like, oh, I can't insist this is missing at random. Yeah, well, convince your supervisor. Like this is MAR enough so that I can use mice to save me from here on. Yes.
Yeah, just a small question. Like, what is this predictive mean matching?
Predictive mean matching, somewhere later. Predictive mean matching is one of the myriads of different algorithms mice can use to help you to guess, to impute, to fill the hole. Depends on what type of categories of data you're feeding into. Predictive mean matching would pretty much inspect the whole column and see what, based on the distribution of itself and others, where most likely you are. So it's not a simple mean, it's not added up divided by n. That's a simple mean, which is this one. That's unconditional mean imputation. So predictive mean matching, you can think that as a fancier version of, because for simple mean, you add it up, you divide by n, you get a point estimate. Where's the standard error? Right. So this is pretty much this, fancier with the standard error. So that's why you have a turbulence, a bit of disturbance. So we will get into how to customize. So the cool thing about mice is you're welcome to, especially for your first experience, feel free to use the default, very sensible default. And I will try its very best to guess what's in your head. Now, if I pulled out this imputation, I just saved it, and I say imp BMI, I can actually inspect what R has done for me. Remember, I have a couple of patients whose BMI information is missing. Patient number 1, 3, 4, all the way to patient number 21. They are missing. Now, R said, I've done my very best. I reckon predictive mean matching is the best method. I did it for you. And those are the 5 parallel universes of 5 versions I have created for you. Please inspect. Make sure that they don't sound too stupid. What about patient number 2, number 5? They don't have missing problem to start with. They are identical in all 5 versions. This is like a very conclusive, like what does this 5 versions look like? They look like this. And you can order each one of them. So BMI, you can change that to cholesterol, and you can actually, it doesn't look too stupid. And in addition, you can actually order the complete data set. So complete data set imp. And if you say, I want to see the second set, the third set, the fourth set, you can run them. And you get the printout of the 5 different versions. Yes?
There was one more question from the chat, but I think this was already partially answered.
Yes.
Right here was the question, which algorithm does the package use? Like the mice package?
It depends on what sort of variable you're feeding into. If your variable is binary, R will try to make the best guess. If it is ordered categorical, it will use a different algorithm. If it's a numeric, so this is all depend on what you're feeding into R. So this is one place that you really want to tell R very neatly about the property, the attributes of each column, because the more you regulate your data set before you feed into mice, the better success R can do to choose the correct method for you. If you disagree with the method R chose for you, you can override it you can specify, and that's 2 slides from now. We'll see how to override, how to explicitly tell R, I want you to use this method for this column, this method to that column. It's definitely possible. Yes, I have multiple questions. If I can start with.
Yeah, so I have 2 questions, if I may. So first, if it's like predicting the missing values, is it forming a regression type of problem using all the other variables and some algorithm and produce the imputations? The second is, if you are trying to take a guess of 5 datasets, isn't 5 too little? Can't you do 100? And how do you specify how different they may vary? Like, for example, for the first imputation, it can be from 20 to 29, and that's a pretty big range, right? So I'm just wondering if, it's possible to control that, and how do you control it?
Yeah, so the comment or the questions we received from the participants in the room is, first of all, how do you control for this, how wide the range is? What R was doing behind the scene? Is that a regression? The answer is yes. Everything R does is essentially regression, isn't it? We try to use as much information as input, and then when we try to give you, especially if you're using, like many of the methods are Bayesian method. So for Bayesian, so you have your prior in, you have your likelihood function, you have a posterior, and then we do a posterior draw from the posterior curves. So that explained where all these 5 come from. It's from the posterior. And how do you control the shape of the curve? Well, it depends on the 2 curves you put into the base. So that is definitely behind the scene. At the beginning, we don't have to think too much about it. But as we become more experienced user, we can definitely fine-tune, open the black box, and we can specify lots of, and we can actually help R by choosing the exact setup. And is 5 too small? Can I do 20? Definitely. Can I do 50? Can I do 500? Computer today is very cheap. It doesn't cost that much. I actually run 5 versus a 50, same amount of time. Right, so if you're unsure, if you feel very insecure, feel free to throw in a bigger order more. So you split your universe into many, like a cone-shaped, like very many parallel universes. Fine. The only cost is computer time, which is very cheap. But if you ask whether there's any theoretical consideration, there's any harm, the good answer is there's no harm. You can always order more. But another good news is, even at small number of imputations, even you say 3, 5, so those sounds like very small. Multiple imputation is already pretty good at 3, at 5. Magic, isn't it? Even small numbers will give you very stable property. In fact, I did an experiment. I start with 3, I override the default into 3, I repeat it for 5, I repeat it, there's no change. And in fact, in the next slide, we're going to try different combinations. One is 5, one is 10, and you notice they differ by 3 decimal points. So it quickly converges, and there's no more benefit anymore. By rapidly increases to 1,000, no need. And in fact, many practitioners advise that feel free to take the default 5, keep going, finish your analysis, and then do a sensitivity analysis by increasing your 5 to 20. It's unlikely anything will change. So that's why mice use 5. It is very cheap, very quick, it reduces the computation load, and it reaches stability already. Hopefully that answered your previous question. Now, R said, I have more questions. Oh, sorry. Yes, I have one question from the room, and I have one more question from YouTube, I think. Yes, go ahead.
So the way you describe the method or the approach that mice uses to determine which imputation method is adequate is based on the data type, whether it's numeric or categorical, etc. But is that the only criteria? It's like just a generic tree where it's just like processes data types with this method, or does it run multiple imputation methods and then based on another, let's say, other objective criteria, it evaluates the extent to which the imputation is reliable across different methods?
I don't think R will do the horse racing and then choose the best, most stable. My suspicion is R is going to inspect your, so if you do str, you do a string, and then you have a look at each variable, what they are. That's the first thing R will do. They will see what this column is, and then go to the checklist. This type, use this as a default, unless you tell me not to. Then I follow your advice.
Okay.
So
the defaults are kind of very, like, so if you have numeric, there's one default only.
one type is one default, and in fact, looks like our participants are very interested in this table. So as you can see, if it is a numeric in nature, R, if you don't say, would preferentially use PMM. If it is a binary, then R will preferentially use log reg, etc., etc. So this is a very one-step decision. It does not go through all of them and choose the most, but it leaves the possibility of us. We can do the horse racing ourselves. But again, how do you know which one is better, right? It's like it's an unknown, and then you just you have to make a decision right now. Do we have another question from YouTube?
There's a few.
Yes.
So, first off, you say that more covariates can pull you out of the mud, but can you use a larger sample of participants to help you with better imputations as well? Or does that depend on how much missing data you have?
As every answer in science, it depends, isn't it? It's rather unsatisfactory, but it all depends. Because what actually behind the data missing mechanism is never known for sure. As scientists, we are rather post hoc. So the best solution, the very honest answer is we don't know. We're open to different configuration, and we must inspect. So that's why you see me spending lots of time on visual. We see, we trust our eyeballs, and you'll be amazed at how reliable or how much information our eyes can give to us. Quite often, always come back, always plot your data. Original, imputed. If you say you've done a good job, show me, right? Mice is there to serve you. You are still the master. You still need to make the decision at the end. And R can only give you enough information. R cannot make such decision for you. So the very honest answer is we don't have the clear, we don't have a clear answer, yes, no. But by using lots of visualization, by using lots of diagnostic plots and tabulation, we can actually inform ourselves as the author. Should we go here? Should we go there?
That's another question. Does mice handle multi-level data structures?
That's our final example.
I take that's a spoiler, and yes.
Yes.
And then there's the last question here. Is there a predicted versus observed comparison for this data?
Predicted versus...
This is a bit back in time, so I'm not exactly sure what it refers to.
Predicted versus actual.
I'll ask for a rephrase in the question, and you can continue to talk.
All right. As I said, because we are in the dark, we are really insecure about it. We really, really want to inspect. Please show me what you've done. So this is what I can do for data inspection. After R said, I filled your hole. So we have 4 variables: age, BMI, hypertension, and cholesterol. Blue, not missing, already observed. Red, they jitter a little so that we can see that they don't all sit on to each other, are the best guesses mice can give us. First impression. There's nothing stupid, obviously stupid here. If you end up, the red is like scattered everywhere. This is a binary variable. You can't have red in between, right? That will be a bad imputation, Right? So this is, at least you can make this judgment. That's not controversial. Okay, the guess follows the same distribution as the original data set. Well, that's promising. And the mix of the red and blue sounds, at least it's not too stupid, reasonable. Right? So this is what you get straight away by inspecting strip plot. I have one question from the room.
Is it always the case? So if I look at this plot, I see that the reds are only where blues are already is. Is it, can it happen that the reds, like the new data, is somewhere where you don't have data yet?
That's it. That's actually going to be one of the fun exercise I'm going to allocate to our participant. I want to see crazy multiple imputations, wrong answers only. I want you to play with different methods and give me the stupidest plots, so that you can see, oh, that's something I do not want, right? Quite often we learn from reading stupid answers. You can actually definitely mess up your MI by either feeding mice the wrong category or by choosing the wrong method. But that's why it is extremely important to inspect. Don't skip this step. Yes?
I was actually asking a bit more about the BMI and the cholesterol, because those are continuous variables. So it wouldn't be wrong if you would put the new data in some value that doesn't exist as a blue yet. So is it like this code, like this package prefers to impute the same that it was already observed, or is just by chance that's what we see now?
So the question is, BMI or cholesterol, you do have minimum and maximum. So we do have the observed range. Can mice produce predictions that are outside of the range?
Or in between?
In between, that's allowed, isn't it? So at least you can't blame mice for producing something in between. It's like anything in between, because it's a continuous numeric. Anything in between would be considered reasonable. If you go slightly outside of the box, then how wrong? Like if you're like 20 units out, maybe we are not very confident. When I was using mice, I am slightly like a 0.1 outside. But again, could that be the true value? It's just like the maximum value that has gone missing? It could be, right? It's not automatic. You are disqualified if you go slightly over. But again, it's judgment call. Mice is there to help us, the scientists, to make a decision. We have to, at the end of the day, make a call. No, this is obviously not, do it again. Remember, we have power. We are the author. We have to sign off on our paper. So this is more of a macro level, the data set level. We want to inspect for immediate suspicious wrong imputations. Like before, we can do this variable level. For example, I keep using BMI and cholesterol because they are both numeric and therefore continuous. I can say, okay, form an XY plot for me by crossing BMI with cholesterol. Then you will get the variable level inspection plot. This is how you read it. 1, 2, 3, 4, 5, 6. The first one, you only have blue, which means that's our baseline. There's no red in it. The first set of imputation, second, third, up to the fifth. We ordered 5 imputations. And that's for each parallel universe. That's the red-blue mix looks like. So as we can see, we are drilled down into this cross and see all 5 of them. Do they look stupid? At the variable level. The previous slide is at the dataset level. Here is at variable level. In this case, all 5 imputations look reasonable. Very quickly, challenge yourself. Produce something shocking, please. All right, enough diagnosis. let's do our final job, what we are paid for, and that is we need to analyze such data set. How do we run, say, linear model, open bracket, say I suspect the patient's cholesterol level is related to the patient's age and his or her body mass index. Right? We have our medical specialist in the room, so there could be good medical reason to suspect such linear model. Now, how do I put this in this context of MI? This is how you run it. We're going to put this original linear model behind expression. So we say with, we use this with clause. With data equals to imp, as from previous slides, many 5 slides ago. Expression equals to copy paste our good old friends LM here. And bracket, save the result. Now, one extra step. This fit is not one result, it's 5 results, right? Because imp is not 1 layer, but 5 layers. So when we order summary, we need to say, we need to put another nesting layer in it. Summary, oh, before we do that, take the fit, 5 versions, please pull it before you give me the summary. That's it. So with, parallel, pull it, back into 1. Now, give me a summary. This is what you get. No surprise. This is almost the same as an original LM. So, what do we have? Intersect, yeah, don't worry about it. Looks like cholesterol has something to do with, oh yeah, age. Looks like an interesting variable. BMI, yeah, looks like an interesting variable. As you get older, your cholesterol goes up. As you become more obese, your cholesterol goes up. Yeah. Well, I don't have enough medical training, but that sounds about right. Right? So this is how the rough idea of how to wrap our substantive scientific question into this MI context. Data equal, expression equal, then do a with. Parallel analysis, then pull, and then display. This is one promise. I said we can actually increase the number of draws. So instead of draw 5 from posterior, can I draw 10? Definitely. For some reason, we use lowercase m in multiple imputation literature as the number of draws or number of parallel universes you want to order. So mice continued this tradition. They say m equals 2. Go crazy. You can order 20. You can order 50. Although previously I already explained, based on experience, it doesn't quite pay that much. It's quickly diminishing marginal return. But if we experiment this, we say, well, can you give me 10 draws? And I want to see how much my estimate differ. At 5, the default is 5. We get 5.383. If you double it, you get 5.384. So they differ by 3rd decimal point. Very, very little. While some estimates, for example, age, actually, there's a big jump, but I suspect that's just a unit of measure. So it may look it's a very big jump, but again, I need more medical training too. I need doctors to actually say, well, is that a big enough, meaningful? Because it's not centered. If I center them, that could also tell me it's like, yeah, it's minuscule. So I suspect that this is a unit of measure problem.
How much missing data can you have in a variable? So would it be, for example, possible with 30% missing data in a variable to go with missing data, or is there some rules of thumbs there?
Good news is there's no limit. You can throw in 99% missing. But what will happen to your 5 different versions? What happened to your 10 different versions? They pretty much cover the minimum to the maximum. Huge uncertainty. So if you cheat mice will cheat you back. So if you throw in very, very sparse, tiny, tiny information, mice will just give you huge confidence intervals. But it's doable. Mice would not say error message and it's more than 30, I'm not running it. It'll run. Yes?
Actually, just a question, because apparently I'm not familiar enough. Where do I see the confidence interval?
The confidence interval point estimates 1.96
Yeah,
of
but
your.
where do I see it in here? That would be standard error?
Where is it reported?
I suspect you can change the, you can customize the output, but I don't know how to.
So it is not in these few lines?
Yeah, I was using the default. I suspect if you dig the documentation more, you can actually change, say, CI equals to true. So you can change the display. But that's more of an option. So somewhere in the documentation, they will be able to tell you. Yes?
How sensitive is this imputation to different kinds of data generative process? Let's say like your like more of a Gaussian distribution, or more like something crazy like a Gaussian, which has no standard deviation. Like, how do these properties of the generative process make it more or less compatible with those imputation techniques?
The question is, if I choose different methods, say I move from Bayes to a non-Bayes, I change from a sophisticated to a naive, say, would the output change substantially? Could that be like a good rewording of your question, or?
It's kind of like the flip side. So like I'm more thinking about the phenomena itself.
Yeah.
If they produce data that is distributed in very funky ways, let's say like given a bimodal distribution, which has some fear how to model a single distribution of things like that. Like how would these funky distribution that you observe be compatible with the assumptions made by these different imputation techniques?
So if mice produced crazy red, right? Red is the best guess produced by mice, and it's clearly wrong, and I still went ahead with my analysis. Would that mess up my entire analysis? Is it? Or how does
Yeah, I guess that would be a diagnosis, right?
choosing the wrong method? How would that the wrong method cause the output to differ?
So, like,
To go off.
Do we need to assume a Gaussian distribution of the data itself, or do we need to make certain assumptions about like what is the limit of this imputation?
So what's the onus, the burden of proof is always on the researcher rather than on mice. So that's the take-home message. We are still driving the car, right? So we need to impose good theoretical stewardship. We need to make informed professional judgment. Should we say Cauchy? Should this be a beta distribution? If you already know this is probability, right? You might want to impose this should follow a beta, which is bounded between 0 and 1. This is a count data. You should use Poisson. So nowhere in mice it takes away the researcher's duty of care. It's still us who must make such decision. Mice is there to make the best guess. Most of the time, the guess is appropriate. But there will be time that human really want to take over. And when we get to multi-level, I pretty much want to kill all this default. I want to set everything to 0 because I want to tell mice, this column is this column is that. So there will be times that, no, I want you to totally go back to 0. Listen to me. Definitely.
Just a question related to this. So like the default, this predictive mean, that wouldn't really be very good with a Gaussian. If the distribution not Gaussian, like if it's with bimodal and you have the predictive around the mean, that would just go off, right? So that's how I should understand it.
Yeah. So if it is already a binary as an input, and R would be wrong in using PMM. But then what happened is you did not set up your column correctly. You didn't specify factor. But if you already say factor, then R will be smarter. R would not produce like a 0.74. R would actually know this column is a 0, 1. Then R will give you only those two.
Is there a way to test the accuracy of mice? So say you have a complete data set
Yes.
and you delete, is there a function in mice where you can delete some of your data and test the accuracy of the predicted missing data?
I don't know. So Herrick is asking, can you do the other way? Can you start with an ideal matrix and then tell mice to mess it up deliberately? And because now we are the one who's playing God, we actually know the missing mechanism. And then that simulation study is actually done quite extensively in the literature to actually test advantages, disadvantages of different algorithms. And therefore, we shall choose this as the safest bet. So that was done before, but quite often is to train our data, to train our algorithm how to make decisions, I suspect, rather than, so that we don't have to redo this. Good. I see another question. Yes.
This is related to the M, when you choose the number of universes.
Yeah, parallel.
Do you split the data into like M parts, or is it some sort of bootstrap approach where you sample like a new data set from the original data set n times?
It's M draws from the posterior distribution. So does that sound like a bootstrap? It doesn't quite feel very bootstrappy, is it?
Yeah, so you don't sample from you have an original data set, you want to create like 10 copies, or not copies, but like layers or universes or whatever. And then do you create these 10 data sets by sampling from the original data set, or do you just split the original data set into 10 different parts, or is it some other mechanism that?
It depends whether the original is observed or missing. If the original is blue, then those 10, no question asked, they are identical. Copy pasting 10 times. Nothing need to be done. But if the original is a whole, then that's where mice gets in. And mice will say, I'm going to take over. I'm going to make my very best attempt by forming a posterior distribution. And then I draw from the posterior distribution how many, you name it, 5, 10. So it doesn't feel quite like just a simple bootstrap.
No, I think I've fundamentally misunderstood how the M thing works. So yeah, I'll probably have to read the documentation later.
Yeah. So it's pretty much we form a posterior, and then how frequently, how dense you want to draw from posterior. So I don't feel this is very good. Bootstrap is pretty much you don't actually cook it. You just from the vegetable basket, you just take vegetables. But then I feel like mice is like cooking it into something, and then they take that from the cooked dishes.
And also regarding the supported model, I see you use a regular linear model. Is there a list of what sort of models do mice support? Can you use whatever, or is it just linear models?
There's no limit.
Okay, whatever.
You can. So the question is, for expression equals to LM linear model, can I throw in generalized linear model? Can I throw zero inflated? Can I throw in? Go for it. Because what mice is doing is pretty much a wrapper. Split, run each in parallel. As long as R can run each in parallel, you have enough information to pull back into a distribution with the correct standard error. Mice doesn't mind, because that's outside of mice. Good to hear. And customizing MI, customizing our multiple imputation, we are pretty much already expert on that. as we can see, we can actually override mice's original or default decision by saying, no, for this one, I want you to use Bayes. This one, I want you to use naive mean. Go for it. You can always, as scientists, we have the final say. We can override mice by specifying each column what we want. Or we can be lazy. Instead of saying C concatenate 1, 2, 3, 4, if you don't say C concatenate, if you just give one command, that means R will use, or mice will use this for every column. Yeah, well, quite often that's a bad idea. Don't do that. What else we can customize it? Polyrec. So if you know yours is already ordered categorical, you can get increasingly sophisticated. So I left one example here. So you can see logreg, polyrec. So that can deal with more logreg and polyrec. So this is for categorical, either it's binary or more than one outcome. So definitely this is doable within mice framework. And it was actually the default if you set up your data set correctly.
Are you familiar with Little's MCAR test for testing missingness, and would you recommend it?
Little, Reuben and Little, those are a couple of names that we hear all the time in missing data literature. Yes, at early stage of the theory's development around about 1970s and 1980s, when computer was not as cheaply available, scientists relied very heavily on Little's tests. There's myriads of tests. For some reason, actually I can conjecture, for some reason, we become increasingly less relied on such tests. That's the trend. My guess is those tests are not, like, they are not quite powerful, they are not quite, and they didn't quite stand the test of simulation and the test of time. So there's a collective decision made within the scientific community. It's like, yeah, we can see why back in the old days those tests were valuable because computer was so expensive back then. But as now everything's so cheap, we no longer need to rely on, plus they suck. We no longer need to rely on those tests. We can actually do more of a visual theory and background to guide us. And this actually once again highlighted the fuzziness with, in the field of multiple imputation in missing data literature. In very few occasions, you have a definite yes/no. Very few. It's all about professional judgment. It's all about us. We scientists need to make the captain's call at the end. We can hire lots of advisors, but at the end of the day, you're the president. You have to press the button.
So you say computation is cheap. Like in some instances, for example, like we work in mathematics where we have like sometimes single cell data which has a lot of like dropouts and empty measures, and we're talking like tens of thousands of cells with tens of thousands of variables. Like, can these methods scale to that level?
Oh, tens of thousands. Can I share my
More, yeah.
Can I share my experience? I have 200. Because I'm doing education research, and then for me, each column is one subject. So under Norwegian education system, like we end up with 200 different subjects, but then some subjects, the whole Norway, only 25 students chose this subject. So I think that's the closest my research overlap with your, it's like a huge, or sparse matrices. If you start with a very sparse matrices, can I naively apply mice? My hypothesis is there's actually extra statistical techniques for sparse matrices. So you might want to consult sparse matrices literature first and see whether you can take advantage of the know-how in that area before you jump into mice. Mice is one tool for not too bad. Like mine have missings, but it's like 30% missing. But once you get into 99% missing, you might want to question, because you can still use this, but you get rubbish. Rubbish in, rubbish out. Totally unusable. Yes?
So you mentioned how long does it take for your 300 samples?
I regretted it. I ordered 50, and it took the whole, and I killed it. So, because I want to try where the like, I tried to do a stress test, and I realized, yes, computer is cheap, but I ordered, because mine is ordered categorical. Where is it? Polyrect. Did I use polyrect? Yeah. So no, I actually ordered logit, and logit is that's like it's a sigmoid shaped, and you don't have a closed form solution, right? You have to use numeric approximation. Extremely slow. Don't order 50. Because I went to the kitchen and then thinking it's going to be done by the time I come back. No, I finished watching 20 YouTube cat videos and it's still not done. So I was just like, yeah, don't worry about it. No, not cheap enough. Yes. Alrighty. Multi-level. This is, I promise, this is the very last slide, and I'm not going to go too deeply into it. Just as to fulfill my promise to some of our participants online, mice can definitely can help us with multiple, with multi-level data. In education, for example, students who share the same school tend to have more similar responses than students who go to different school, right? So you have these students nested in school. Schools are nested in region or country. In education setting, say large-scale international assessment, PISA, TIMSS, we very naturally consider multi-level. Can mice do that? Definitely. Then what happened is you need to specify, you need to tell mice which column is your level ticket, level 1, level 2 ticket, say the school ID. And we use -2 for some reason. So this is the time you want to turn off everything. You turn off the default.
Zoom in on the
So let me. So when we get to multiple, when we get into multi-level, remember this magic number -2. That is how you tell school ID, so that mice would know. This is your level 2 marker. And then we have 1 and 2. So that is the fixed effect and random effect, how you want R to implement. I was using this very typical popularity. When I was learning multi-level, and Ronnie was using this, and yeah, everybody gets so sick of it. So, but then it is so well known. So it's a pupil's popularity. We have teachers' experience. We have teachers' gender. So that is the data set. I actually gave, I think I left enough reference on the, so if you go to page 21 and page 22 of the manual, they actually gave quite extensive background, which I will not regurgitate here. If your research is multi-level in nature, you can start from where we stopped today. As you can see, multiple imputation is a fascinating and productive field of literature that there's definitely, we still left lots of stone unturned. There's lots of, for example, if you have censored, truncated data, zero inflated, Poisson process, how do you do that? It's all doable thanks to the very philosophy of separating a complicated research question into the missing data part. Let's do that first. Set it up, tell mice what is what, which is fixed, which is random, which is level 1, which is level 2. Do that for me. order how many. Now, no more missing data. Let's go back to science. And we end up with valid, correct standard error. And that's the takeaway or the light at the end of the tunnel. So before I go, I wish to share with our users.
Question, if you go back.
Yes.
Like here in the mice command, you have introduced the maxit.
Which?
In the first line there, you have like
Max is equal to 0.
Maximum iteration.
Yeah, so I was wondering like number of iteration contra how many planes or data sets you should have. So I see could you just increase that instead of and still keep it like 10 data set, but then have 100 iteration for missing values? And then I don't know if that saves any computing.
So we have one question from the room, and that is related to this option max it. Max it means maximum number of iteration I want, because what mice is trying to do behind the scene is actually simulation. Yeah, there's MCMC, there's da-da-da-da-da, you name it, all the fancy techniques. So maximum iteration, here I say maximum iteration equals to 0. This is actually almost like a fake mice. What I want to do is I don't want mice to actually do any work. I just want to extract the predictor matrix so that I can turn it off, I can kill it, so that I can impose my version. That's why I use maximum iteration equals to 0. Don't bother, just give me the matrix for me to kill. But the good question is, previously, can I specify maximum iteration? You didn't even see me specify maximum iteration because I relied on mice's default. Simulation study actually showed it's more than adequate. So it's a very sensible default mice is using. Definitely, we can jump in and we can increase the number of maximum iteration, but the marginal, the incremental return is minuscule. That's the very honest answer. And I suspect there are actually simulation study that is done. If you double the maximum iteration, does that change anything? Not even how many decimal points. So it doesn't look like changing max it is a productive way of improving our result. And we don't even know whether we're improving anything at all, because in the field of MI, we don't know the answer. We don't even have something to compare. The only way is we start with the full data, and we artificially we mess up data, and then because in that case we know the true answer, and then we see which one is promising. Doesn't look like the field has focused on manipulating maximum iteration as a solution. So I guess the answer is there's a reason. So if I can share this little paragraph, this is one resource I copied. I stole from Van Buren. Van Buren is actually the author of this mice package. So 2 authors, he's the leading author. He's also a very productive writer in the field of missing data and psychology and psychometrics. So if you actually search Van Buren, I think it's stephvanburen.name. That's his personal website. Very productive author. So he actually, based on his many years of practice, gave us this starting point, this template, right? We conducted our step 1, missing data analysis. Step 2, substantive research question. Now we are ready to communicate back to the wider audience. What a marvelous template. The percentage of range between in a total of how many observations, how many gone missing. In particular, women or girls and older girls tend to have more missing. And I ordered 40, m equals to 40. I used mice 3. I think now we're in 3.14. Pi 3.14. And we use that because methodologists currently agree this is the state-of-the-art approach to missing data, blah, blah, blah. And we then put everything back using Rubin's rule. So very concise and good writing. Feel free to steal it in our own paper. Lastly, I compiled, this is my personal collection of literature. This is only the first page that covers not only today's reference, but also a couple of extra references even didn't show up earlier, which I consider them to be super useful should our community needs more help and more in-depth methods. This page can serve as a starting point. So I hope this is first experience 2 years later, and I hope my story is an interesting one, and I hope everybody a very success in your research. Thank you.
Is there any questions before we start?
Does it have anything to do with the causal inference nowadays, like that? Do you have any, give it any hypothesis before you do the imputation?
So the question is causal inference.
Yeah.
Can mice integrate really well with causal inference? Mice is more of a tool, a mechanical, correlational, two curves fusing to one. It is not causal in it by birth. If your research question is causal, difference in difference, instrumental variable would be pretty much the front door approaches, and you have your backdoor approaches. So I feel that causal inference, especially in medicine, especially in social science and in economics, for example, does rainfall causes mental health? So that was one paper published back in 2014 using Indonesian census data and Indonesian meteorology bureau data, and that is a different path of literature. You have to be very smart in your design, identifying your instrument variable. While mice can give you, should there be no missing, the likely numbers are, can you take that as a counterfactual? My honest answer is I don't know. Personally, I would not escalate this into a counterfactual statement because my feeling is counterfactual is a big job. Extraordinary claims needs extraordinary evidence. And I don't think mice, being Bayesian, being is causal by birth. Any free questions?
Maybe just a comment
Yes.
on missing data and causal inference, because I use it in a very different field. I also use Bayesian methods, and there also sometimes you see missing data being handled in a way where within one model you define separate, let's call it sub-models, that could explain the missing data. So you are trying to predict the missing data as part of the same model. But as you said, there are different ways of handling missing data, and it really depends on your very specific problem, and not the least on what's common in the field of research to a
Thank you.
certain degree before you can make a judgment. So
Thank you.
it's not an easy ground.
Exactly. So there's thank you for pointing out. MI, yes, it is generally applicable at the start, but very quickly we form our own little tribes of flavor of MI. I'm from economics, econometrics. That was my bachelor and my master. So I'm from the business pathway. So we perceive this Bayesian and now I'm in education, and distinctively I can feel that's two different wings of philosophy, and we actually treat data differently, and we think the causal, the philosophy differently. And let alone we have medicine, let alone we have genetics. I won't be surprised if different field actually developed your more subject-specific flavor of MI. So today is only the invitation. So we know roughly we start, roughly we split the universe into parallel, roughly we run that in parallel, and then eventually we come back. That's all. So at the end of today, I'm not claiming we can solve every question in the world. That would require a lifelong learning, but that's such a fascinating invitation. So do consult your field and see what prior research and what prior literature and procedure, say sparse matrix. You can't be the first person who asked this question.
So last final question, and before we wrap up, what do you think about the package JOMO?
Yeah, so there are multiple, more than one packages in our community. JOMO is a joint modeling. So joint modeling versus so chained equation, that's two different genesis, two different historic pathway that was explored by prior researchers. Say, I think it's Schaefer. So Schaefer 1997, that's another major landmark publication. That is the joint modeling approach, while little Rubin was using this chained equation approach. So that's two different approaches. If consensus is signaling something, joint modeling is no longer the dominant approach. Now the feeling is multiple imputation is the only game in town. I'm not a mathematician by training, but I suspect the mathematicians actually run too many years of horse racing and competition between joint modeling approach and this chained equation approach, fully specified conditional approach. And then gradually, people vote with their feet, and we end up in this club.
We're going to stop the